Okay, so good morning and good afternoon, everyone. My name is Eduardo Suarez, and I'll be your host for today's webinar. I'm joined today by my colleagues Obi Remen and Roxy Cardo here from our Customer Experience Center in Melbourne, where we showcase the latest innovations from S&C to our customers in our region. So before we begin, I'd first like to acknowledge the traditional owners of the land on which we stand today, the Boon Wurrung and Wurundjeri people of the Kulin Nation, and pay my respects to elders past, present, and emerging. Today's webinar is on the benefits of large-scale deployments of reliability improving solutions. This is part one of our 2022 webinar series, with the second part occurring later this year. Just so you're aware, this webinar is being recorded, and a link to it we made available at the end of the presentation on S&C's website. Before we go on, just a quick housekeeping. At the end of the presentation, we'll be holding a Q&A session. There is a Q&A button on Zoom, so if you have any questions during the presentation, feel free to go into that Q&A button and lodge your question there. We'll be getting to them at the end of the presentation. So with that said, we're obviously presenting on behalf of S&C Electric Company. And if you don't know, S&C has a long history of over 100 years in the electrical distribution and transmission industry, with over 60 years of activity here in the Australian and Asia Pacific market. We're specialists in switching, protection, and control solutions, with solutions bringing a focus to reliability to network operators, renewable interconnections, mining industries, and other commercial distribution complexes. So just as we start, I'm going to launch a quick poll just to get our engines going. You should see that poll popping up to you. And the question is, who invented the first reliable medium voltage power fuse? Was it Edison, Faraday, Tesla, or Schweitzer and Conrad? See a few questions, a few answers coming up. Ooh, a bit of a split. Okay. So I think many of you have seen this coming. The right answer is Schweitzer and Conrad. If you didn't guess it, that's where the letters S and C originally come from. In the very early days of S&C, the medium voltage liquid filled power fuse is where our company started. So that said, let's get right on to our presentation. So the agenda for today is we're going to be covering primarily three things. The first of them is I'm going to be doing a very quick introduction to where do reliability issues come from. My colleague Obi will be presenting to you on new practices for implementing reliability improving solutions and what that is. And Roxy will follow up from that to discuss a little bit on how much of a difference do these new practices actually make. So just to create this shared common understanding of reliability, particularly obviously in the electricity industry, reliability is the ability to receive power or get power into homes in a constant fashion. So obviously there are things that can go wrong to prevent you from receiving power in your homes. And those can happen behind a meter. So it can be a problem in a house or a industrial facility. They can happen on a generation plant, simply stop working or have stability issues. Problems can occur in transmission lines, and they can also occur in distribution lines and distribution assets. Now, if you look at the spread of that, particularly taking numbers from here in Australia from the Australian Energy Market Operator, although power stations, every time they go off, they make the news, the reality is the majority of interruptions are caused by issues in the distribution sector. So about 95% of all the faults generally occur in the distribution area. Now, with that said, I also like to create some common understanding in some of the wording we're going to be using, particularly when it comes to faults, interruptions, and temporary and persistent. Now, these have a cause and effect relationship. First, a fault is a cause to an issue, and they can be classified as two. Particularly a temporary fault could be a wildlife issue or a wind clash of two lines. In other words, there is a fault for a small period of time and it gets automatically cleared. A tree branch falling on a line and then falling on the ground is another good example. The persistent faults is that which requires human intervention to be fixed. So we're seeing here a tree falling on a line and completely destroying that line. We can have a car versus pole situation, which is very similar. Now, what we expect is that temporary faults like that wind clash scenario would cause, we call momentary interruptions. So that's the effect, that's the outage. Momentary meaning anywhere less than 1 to 3 minutes, depending on where you are. And we'd understand that persistent faults like a car versus pole we mentioned before would cause sustained interruptions, which require someone to go to site and fix the issue. So a long outage. However, the way we protect distribution networks today, and traditionally with fuse blowing protection schemes, where we use fuses to protect laterals, tee-offs, and transformers, they do their job and they protect the network by sacrificing themselves. However, they have a very interesting downside, which is they turn what is a temporary fault, like a wildlife issue, into a sustained interruption. They require human intervention to go and replace the fuse. Now that we know the majority of faults are in distribution networks, how many of them are considered sustained or transient? Well, this is going to be different from depending on where you are in the world, but particularly today, if we look again, focusing on the Australian energy sector, we can look at all the data from all distribution networks here, and we can classify the faults of the distribution network into asset failure, overloads, third-party events, weather events, vegetation events. And in reality, what we find is, on average, roughly about 56% of all the faults seen on distribution networks are what we call transient faults. Now, this is the average, which includes networks that have a lot of underground networks not exposed to these events. So you can expect to see anywhere from 70 to 80% of faults being transient, being quite common on distribution networks. So now with that understanding, I'd like to call Obi to join me here in the podium as we will continue this presentation.
Thanks, Eduardo. Hello, everyone. My name is Obaidur Rahman. I'm application manager with S&C. Before I get into my part, I would like to start off with a poll. So the question for the audience today is, how long, launch it first. Okay. How long does it take to deploy a new technology on distribution network? You think it's 3 months, 6 months, 1 year, 2 year, or a 5 year? So if someone comes to you or you realize there's a new technology in the market that you can use to improve your reliability or protection, how long does you think normal process takes to system-wide deploy that technology? Give a few more seconds to our audience and then close the poll. Okay, you have 5 more seconds. Thank you. And I'm just going to share the results with everyone. So, okay, 35% of our audience believe that it takes almost 2 years for a new technology to be deployed on your distribution network. 20% thinks 1 year, 20% thinks 5 years, and 25% thinks it's 6 months. Well, it varies between how quickly you can go over the process of a trials and then move towards a system-wide deployment. And that's where we're going to discuss that how we have improved of the period of time to move these processes quickly for new technologies implementation on the distribution network. Okay, before I start, as Eduardo mentioned, that 80% of the faults that exist on a distribution network are temporary. And when there's a temporary fault on your feeder, a typical recloser will go through its cycle of tripping and reclosing. And when on a feeder, a typical recloser goes through that cycle, it exerts the full energy of the fault onto your network, which means that your assets that are a network, that are your sensitive assets, can get damaged because of that fault energy. But The technology that I'm presenting here today is Intelrupter Pulse Closer. It uses 95% less energy while it's testing for the fault. It's not reclosing onto the for a temporary fault. It's just testing for the fault, and as a result, it's subjecting your network to 95% less energy, and that helps you to improve that feeder reliability and protection. That's that's not all the advantages that it brings onto your system. In fact, in a closed loop system, Intelrupter can use its voltage sensing to isolate a certain section of the feeder during a fault. And if you use as a normally open point, it can restore power to the unfaulted section by just using the voltage sensing technique. So you don't have to use any communication for that purposes, but Intelrupter just using the voltage sensors can restore the power and improve reliability on your feeder. As we go further away from your main feeder, you have your lateral and swerve protection. And usually on those lateral and swerve protection, you have fuses that are protecting your these lines. And as we all know, fuse is a simple our current protection device. It cannot differentiate between temporary and a permanent fault. So what happens in the case of a temporary fault, even that occurs through a intervention of a life of a wildlife, or as a result of a major environmental event such as like a windstorm or a dust storm or any other storm, you will see that those temporary faults converted into permanent fault, resulting in a distribution of the power, in a disruption of the power for your customers. But if you have something like TripSaver 2, which is a cutout mounted recloser, which has ability to go through a stripping and reclosing cycle for up to 3 cycles or 6 times, it can actually improve your reliability, because in an event of a temporary fault, you will not see a permanent outage. All you would see is a temporary outage for some seconds until it's go through its cycle of tripping and reclosing. And what that happens is basically when you replace a fuse with a TripSaver 2, you're enhancing your lateral or swerve protection or reliability onto your network. The last device which I'm going to talk about in terms of the new technologies is for your grid edge protection. This is for your tail and transformer protection, where again you would have some temporary faults. You're feeding 1 or 2 customers at the end of your grid. Here you would also have a fuse, and again, as discussed, fuse cannot differentiate between a temporary and a permanent fault. Here we have vacuum fuse, self-resetting interrupter. It has a vacuum interrupter inside it. So in an event of a temporary fault, the vacuum interrupter inside the vacuum fuse 2 will trip and reclose after a preset time. And if the fault is permanent, it will drop out to give you a visible indication that the fault is further downstream to that particular device. The difference between a TripSaver 2 and a vacuum fuse is a number of reclosing cycles it can go through. TS2 will typically go through 3 cycles, but vacuum fuse goes through one reclosing cycle. So all these technologies, whether it's a feeder end or a lateral or a grid protection, or at the edge of your grid, helps you to improve your reliability with different methods and different applications. These technologies have been in practice, or they've been implemented all around the world for more than 10 to 15 years in different parts of the world. But what happens when a customer who is new to this technology would like to implement these technologies on their network? What used to happen six months or a year ago, that's why we're using the concept of the alt process. I'll walk you through the process. What used to happen is basically the customer would come to us with a challenge saying there's a reliability issue or there's a protection issue on our network, and we'd like to see what this device is and how these devices can help us or improve our network. And then the technical team will get involved from the customer side, from our side, and we'll do a technical evaluation, which would include how these devices can perform from technical standpoint, from protection standpoint, and how they can be integrated within the existing set of technologies or devices you have on your network. From there will be involvement of different departments, such as your operation and maintenance, and your standards team, and then we will select a site that has most number of faults based on your previous OMS data. Then you would need So of course, you would need some time, 6 months to 1 year. Typically, we have witnessed in our experience. And in that time, there will be different faults happening on the selected sites. You would need to have your resources or someone to go collect the data, analyze the data. You do the commercial analysis and you present it to your leadership or the top of the management, and then you eventually go to a system-wide deployment. And this whole process would have different departments involved during the process, which would elongate the process, which would make it complex over the period of time. And some of the trials would last for 2 years. And what was happening in the old process was not only it was time consuming, it was also lengthy, it was complex. And we've seen in some of the cases that customer was having monetary losses in a way that by the time they would have done the trial and realized what operational maintenance and also monetary benefits bringing onto their network, they would have lost 1.5 or 2 years of time for which they could have reaped those benefits. So the old process would come with all these challenges. But what happened in the past 6 months or years time is there are tools available to us that we can use to bypass some of the steps in that process, which will make this process more linear and help our customers to reap the benefits earlier with these new technologies than later. So I'm going to walk you through to the new process. In the new process, of course, some customers would have their challenges. We can address that. There will always be a technical evaluation depending upon how you want to do it. Some customers would like to do the bench trials. We can assist them. Some would like to do secondary injection testing on those devices. We can, of course, assist them with that. The additional process that we'll add here is we will require a GIS and OMS data from the customer. And I'll show in the next slide why would we need that, because the new tools that are available to us using your data would help us to bypass some of the processes. And the processes we're going to bypass are basically the site selection, the wait time, the commercial, and the data collection, and the commercial and the technical analysis. And what we do instead of them, we'll go through a change management in the organization, which will tell all the which include different trainings for the line crews, familiarity with the product, and other procedural processes that we need to go through with the line crew. What it does is basically it bypasses a part of the processes, and we can do that in parallel. On the one side, we'll be looking at OMS and GIS data, analyzing your network, and the other side, in the parallel, we'll be running a change management with our customers. And that will eventually lead to a quicker system-wide deployment than being involved in the trial process for a period of time and then moving to a system-wide deployment. And this eventually will help the customers to reap the benefits earlier than later. So what is that process? What is the tool that is available to us that helps us to bypass some of the processes and move this at a faster track? The tool we use is called OBI. It's a web-based reporting tool that enables users to analyze and report on data stored in various sources on a one-off repeating schedule. It provides a comprehensive business intelligence platform that offers a full range of analytical and reporting capabilities. This OBI receives the data from the customer, and we analyze that data. And if I show you how it looks like, so this is a snapshot from the OBI. This is a project we did. This is a sample project that we're using for demonstration purposes. So there's a lot of information available on that screen, so I'll break it down for you. So what you're doing with an old process is basically going through all those processes to find out which locations you would like to install those new devices that can improve your reliability, and how much it's going to cost you, and what is the benefit you're going to get from that. And that all can be summarized on this one tool. So if you focus on the screen on the right-hand side, you can see that this network has 22,599 fuses. And if you look at the heat map at the bottom, you'll see that it's showing that where the problem areas are, which are the laterals or feeders where you have fuses that are causing a nuisance tripping. in an event of a temporary fault. And you can see that 1.1% of those 22,599 fuses would require to be replaced with a cutout mounted recloser, which is a trip saver 2. And that would avoid you 651 outages. And the annual cost for that is basically 119K with a truck roll cost of 521K. So what it's showing you, it's accumulating all that data for a 4-year time. This one is particular for 4 years time, and showing you that, okay, these are the areas, you don't have to install that on all the network, but these are the specific areas that would need the new technologies or new devices to improve your reliability. And there's a lot of other information available on this page. You can summarize based on your district. You can choose from the circuit that you want to look into. So if you select one of those circuits, you can only deep dive into those. You can have a summary of the circuit, that what is the contribution towards your CMI, what's the contribution towards your total SAIDI by these feeders, and then you can dig down deep into the device-wise, that which device is causing how much trouble or which device is tripping how many times. So with this new process, we can go ahead in time and realize that, okay, these are the benefits that we can get. And rather than going through a trial period, you just go through a change management period in parallel to this analysis, and you can reduce the time of system-wide deployment that can be reduced from 2 to 3 years up to as quick as 6 months to a year. And the reason why we say that is we recently have a case study from a Western Power Distribution, which is an electricity distribution network operator for the Midland, South Wales, and the Southwest. They had 1 year of trial with the 27 trip savers on 10 different sites. And they realized that over the period of the trial, 80% of the faults were temporary, which helped them to save 16 trips to the site. And these 16 trips, you need to keep in mind that it involves fuse inventory, it involves the truck roll cost, and it also involves the carbon emission with every truck roll that is associated with that. So with this, not only they have same operational costs, but also they have saved 149 kg of CO2 emission for every time for the entire period of the trial. So in order to conclude this segment, the message that we wanted to get across is these technologies that I've just spoken about have been implemented all around the world. They are proven technologies. And for that, since we have new tools available that can streamline the process, you don't have to go through a trial process anymore. We can use these data tools to assess what your problematic areas are and how these devices can be used on those areas to improve your network reliability and protection. And with that, I will hand over to my colleague Roxy, who will talk about different business case scenarios. Thank you.
Thanks very much, Obi. Hi, everyone. My name is Roxana Pato, a senior consultant within the consulting and analytical services team here at S&C. Before I begin my segment, I am going to open a poll, our third poll for the day. Sorry, just having a little trouble getting it up. Okay, here we go, poll 3. So if you are looking at justifying the cost of new protection technology solutions, which of the following factors would you consider? So would you consider truck roll costs, regulatory incentives, lost revenue, or all of the above? So I'll give you about 30 seconds to answer that before sharing the results. at 10 seconds to go. All right, great. So here are the results that you have come up with. And if you say all of the above, that will be correct. And we'll go through that shortly. Okay, so in my segment of the webinar, I'm going to be highlighting the business case differences between the old approach and where we have the trial first initiated by a large scale deployment of the protected devices versus the new approach, where we have a large scale deployment upfront using the OBI application populated with past outage data to identify the worst performing laterals. So just by looking at this timeline, you can see that the new approach allows utilities to realize the full monetary benefits of the selected solution straight away, whereas the old approach realizes the majority of its benefits following the trial period. For this webinar, we're going to use a utility's worst performing feeders, which was suitable for a large scale deployment of 3 single phase lateral reclosers. So for the old approach, the trial deployed 30 single phase lateral reclosers for a 2-year trial period, followed by an additional 1,530 single phase lateral reclosers following the trial. The new approach, on the other hand, deployed 1,560 single phase lateral reclosers straight off the bat. And the unit numbers that you see on the slide is what I will be using in the business case examples that I'll go through shortly. Then at the end of my segment of the webinar, I will again return back to this timeline to illustrate with some numbers the differences between the old and the new approaches. So the business case or cost benefit analysis for any reliability improvement strategy, regardless of being the old approach or the new approach, has some key elements that need to be considered. So each business case takes into consideration costs. So in the example to come, I will go into what makes up the costs of the selected protection strategy. I'll go into how we quantify the benefits by looking at truck roll savings, which are an operational expenditure, or OPEX for short. Another benefit is in avoiding revenue loss, but I'm not going to go into this as it's very small relative to the OPEX savings. However, in some countries where truck roll costs are low and energy costs are higher, the revenue loss benefits will be higher and therefore would need to be considered. Also, incentives such as stippers here in Australia that are available can be used to strengthen the business case. So I'll share a little bit more about the stippers a little later on when we get to that segment of the webinar. All of these benefits justify the total capital cost of deploying a particular protection strategy. And then once we know what the costs and the benefits are what they're defined over the period of assessment, I'll show the outcome of the cost benefit analysis by assessing the number of years over that it takes for the costs to be covered. So this is known as our payback period. So the first element of the business case consider our costs. So as an example, our strategy is to deploy 3 single phase lateral reclosers across 520 sites for a particular utility. The capital costs associated with deploying 3 single phase lateral reclosers at each of the 520 sites is made up of the costs indicated in the table. So this includes our installation, the units, including the installation, risk, overheads, and associated engineering and protection studies. So the total capital cost of deploying this particular strategy is around $5.6 million Australian dollars. So this will be the cost going forward that I use in the business cases. And just so you know, all the other costs are going to be in Australian dollars going forward. The next thing we consider are benefits of deploying the particular lateral recloser protection strategy. So there are several benefits with this strategy that will be considered when assessing the business case. The first input is the utility truck roll savings. So truck roll costs are considered an OPEX or operational expenditure. So the truck roll costs per event, assuming a light utility truck is used, is approximately $1,600 per event. In the table shown, I've indicated the breakdown of this truck roll cost. This is made up of the total cost of the truck used over 6 hours to account for traveling up and traveling back, as well as the time spent on site. We assume 2 crew members go out to attend to the outage. So when you do the math, you see that this comes $1,600 per truck roll event. So I mentioned that this cost was for a single utility truck, a light utility truck, but if instead a single bucket truck was used, then the truck roll cost would be around $1,900 per event. But for the purposes of this webinar and being conservative, we'll stick to the light utility truck. So then once we know our costs and yearly benefits, we can use these to determine the payback period in years. The payback period essentially determines how long it's going to take for you to pay back the initial investment or capital cost of a particular solution. So it's calculated by getting the total costs and dividing it by the total yearly benefits. And utilities like potential solutions where the payback period is as short as possible, ideally less than 5 years, to align with the regulatory reset period. So now we're going to go through a couple of business cases. And the first one is our simplistic business case for a large scale deployment using the new method where there is no trial period. In the simplistic business case, we only need to consider the benefits associated with avoiding truck rolls. So our assessment using OBI has determined 52 worst performing feeders with an average of 10 spurs per feeder. So this meant that a total of 1,560 single phase lateral reclosers can be deployed to improve reliability. On average, customers on the spurs of worst performing feeder are currently experiencing 6.72 interruptions a year due to temporary faults. The number of interruptions was calculated assuming 70% of customers are on spurs, and that 80% of all the faults are on spurs, and of those, 80% of them are temporary in nature. So previously, I indicated that a single truck roll cost was $1,600 per event, which means the yearly truck roll cost is around about $1.7 million. And we previously determined the total cost of deploying 1,560 single phase lateral reclosers, and this was almost $5.6 million. So looking at the simplistic business case on a 6-year timeline, year by year, we can see that our payback period can be calculated by getting the total costs and dividing it by the yearly $1.68 million truck roll saving. So we get a payback period of around 3.3 years, or roughly 3 years and 4 months. In practice, the business case of any particular solution like the lateral recloser is a bit more detailed when looking at it year by year over the designated evaluation period. In this detailed case, we are again using the new approach for a large scale deployment and are including some metrics, additional metrics. So CPI, Consumer Price Index, of 2% is one that we're applying, and the weighted average cost of capital of 4.73%. So for those that don't know, CPI just refers to inflation, meaning the cost of living is increasing by 2% per year, and the weighted average cost of capital is like the interest rate for money that you borrow from a bank. So again, we're assessing over 6 years using our new approach, installing 1,560 single phase lateral reclosers to eliminate those temporary faults. So now we're referring to each cost or benefit in our table with a preceding PV, which stands for present value. The concept of present value is applied to all future cash flows and takes into consideration our CPI as well as our weighted average cost of capital. So we can see that the value of these benefits is slightly lower as we move from year to year, and this is because of the effects of both CPI and weighted average cost of capital. In the same way as we previously showed, we could calculate payback period, which ends up being around 3.4 years or roughly 3 years and 5 months. So this is the detailed case with no incentives. My next business case is going to look at the detailed case with incentives. So it's a good time now to go over what the STIPIS is. So the STIPIS, or Service Target Performance Incentive Scheme, there are incentives that are available to utilities in Australia. The STIPIS is either a reward or a penalty to electricity distribution networks based on network reliability. DNSPs reduce their revenue at risk by either reducing their penalty or increasing their rewards through improving their reliability metrics like SAIDI and SAFE and MAFE. As stipulated in AER's 2018 revision of the STIPIS determination, and considering the time value of money, the monetary impacts or the benefits of STIPIS to the utility are realised in the year following the network investment for a period of 6 years. So now I'm going to go into the business case, detailed business case with incentives, using the same, the case that we had been looking at previously. So 1,560 single phase lateral recloses deployed by the utility to eliminate temporary faults. Again, we're using CPI of 2% and weighted average cost of capital of 4.73%. As you can see, the present value OPEX avoided from truck rolls is the same as what we have previously gone through. The next two lines are our present value SAIDI and SAFE incentives from STIPIS. As you can see, both benefits are calculated from year one onwards, as you have to wait a year to realise the benefits after you deploy that particular strategy. The summation of the present value OPEX avoided and the two STIPIS incentives each year gives our total present value yearly benefits. As an example, what I've shown here highlighted on the slide is for year one. So the total yearly benefit realised in year one is approximately 28.7 million. The payback period then ends up being around about 0.19 years or less than 2.5 months. And finally, present value ratio, or PVR, is another metric which utilities use to determine project favourability, and is calculated over a period of 6 years because this is the period that utilities can keep the benefits to itself. PVR divides the net present value benefits by the costs. So the lower the PVR, the lower limit of PVR is about 1.3 on the basis that the investment will be paid back in 6 years. So PVR values exceeding 1.3 by some margin would make the project favourable. In our case, our PVR value is 29, which is significantly over the limit, over the lower limit PVR value of 1.3. Our PVR is particularly high because we're focusing on the worst performing feeders, which benefit the most from reliability improvement due to the lateral recloser solution. So that brings us back to this timeline where I will finish up by comparing the old and the new approach using the more detailed business case, which includes our CPI, weighted average cost of capital, and incentives. So you may be wondering, why do we have an 8-year timeline now? And this is because the STIPIS incentive benefits for the trial units commences the year after they're installed and continue for 6 years. Then following the 2-year trial, the utility goes ahead with a full-scale deployment in the second year. So the STIPIS incentives benefits commences for that number of units the year after that for 6 years onward. So the 2-year delay between the trial and the large-scale deployment mean that the STIPIS incentives will take us through to 8 years. The new approach with the large-scale deployment upfront considers STIPIS benefits for 6 years, then the last 2 years end up just being the truck roll benefits because the utility or the network service provider is only allowed to keep STIPIS benefits for itself for 6 years. So referring to the unit numbers that are shown on the slide, the old approach initially deploys 30 single-phase lateral reclosers as part of the trial. The STIPPers incentives commence the year after the 30 units are installed and result in almost 1.1 million in combined STIPPers incentive and avoiding truck roll benefits during the first 2 years of years of trial following their installation. If the trial is followed up with a large-scale deployment where a further 1,530 single-phase lateral reclosers are deployed, what we realise is $104 million in benefits from years 2 to 6, which is a combination of truck roll savings and SAIDI and SAFE STIPPers incentives for the combined 1,560 units deployed. And then we have $47 million in benefits in years 6 to 8, which are from the remaining units, which is the 1,530, still within the 6-year STIPPers benefit period, as well as truck roll benefits. So the total savings for over the 8-year period from the old approach, take into consideration the install cost of units, ends up being $147.1 million. Then on the other hand, with the new approach, utilizing the OBI software and doing a large scale deployment of 1,560 single phase lateral reclosers straight off the bat, we realize $163.6 million in benefits and a total savings after considering install costs of the units of $158.1 million. So this is actually a difference of around $11 million between the old and the new approach, or roughly 7.4% extra savings. And this shows that by choosing the new approach, the utility is realizing far greater monetary benefits. The first 6 years after deploying the units, the utility will realize the STIPPers benefits for itself, and then thereafter the utility will share the benefits with the customers, and the majority of continued benefits will come from avoiding the truck rolls. Aside this, the new approach allows the utility to improve its reliability right across its network, leading to improved customer satisfaction sooner. So in summary of the comparison between the old approach and the new, the old approach deploys a few units for a trial over a couple of years, analyzes the results in the report, and undergoes a large-scale deployment. The new approach does not carry out a trial. Instead, the OBI tool using past outage data is used to determine the worst performing feeders, and this assessment leads to a large-scale deployment upfront. In the example that I went through, the monetary difference between the old and the new approach was an additional $11 million, or an extra 7.4% in monetary benefits to the utility by doing a large-scale deployment upfront using the OBI tool. So with that, I will hand back to Eduardo, who is going to summarize today's webinar and moderate our Q&A. Over to you, Eduardo.
Thank you, Roxy. Thank you, Obi. It was a lot of good information. As we now start to slow down and bring this webinar to a close, I'd just like to spend a couple seconds to bring your attention to the 3 key takeaways we have from today's session. The first of them is that traditional lateral protection schemes are heavily centered around the use of fuses. And if we combine that with the fact that the majority of faults are transient, these lead to significant reliability issues and sustained interruptions. That's the premise for today. The second one is that trial processes, like Obi has described, are lengthy and have been traditionally the way that we introduce new technology, almost as an R&D project, particularly in the electricity industry. However, those have the same goal as the new approach we showed today. And for proven technology, the strategic adoption, similar to an OBI software and the use of heat maps and financial suitability analysis, can help businesses and utilities reach the desired results a lot sooner. The third and the last key takeaway from today is almost a break in stigma, that simply by reducing a single year or 2 years of improvements in deploying those reliability improving technologies could represent millions of dollars of saving and financial returns. So with that said, I'd like to welcome Obi and Roxy back into the podium, as I see there's quite a few questions and a few questions on chat as we start our Q&A. So if you joined halfway through the webinar, feel free to add your questions on the Q&A button on Zoom, and we will go through them one by one. First one is from Raymond Asana. And the question reads, for the business case developments, do you also consider the VUS or value of unserved services? I think this is a question better asked by you, Roxy.
Yeah, we consider the SAIDI and safety improvements as a result of avoiding the temporary outages by deploying these technologies. So
that's great, thank you. If you have a backup question from that or a follow-up question, Raymond, feel free to add that in. The second question we have up here is from Mr. Rodolfo Abad, a clarification on the truck roll savings. Does it mean that if the interruption is momentary only, there's no need to dispatch a truck to investigate what may have caused the fault? I think this is perhaps better answered by OB and myself. I'll take a stab at this. If I understand your question correctly, Mr. Rodolfo, that is more related to utility practice than not. What a momentary interruption or momentary fault would relate to is something that would clear automatically. So not necessarily needing the utility to go and fix anything immediately. So they can delay the go to site for say an annual or biannual inspection, for example. I know some utilities will have a practice to go to site every time they see a fault, but that's not necessarily the case for all of them.
I agree with that. And I think the other thing is, again, depending on the utility practice, if you keep on seeing the temporary fault in a particular area or a device continuously at a particular time or at a particular level of the current in your network, then you can probably investigate. But the idea is to avoid those truck rolls for unnecessary operational costs, which devices can help you to reduce. Hope that makes sense.
Thank you for those questions. I think those are the only two we have. Give another minute if anyone wants to ask any other questions. Otherwise, I'll take that minute to say thank you for joining the three of us. Thank you for both of our presenters for helping us out. And as I'm saying that, we do have another question. I believe it's just the repeat from Ray. Okay, so I think with all that said, as I said, thank you very much for joining us. Keep an eye out for the second part of this webinar, and you'll receive an invite shortly. Ooh, this is a good question from Raman. It did not observe monetized safety improvements rather than just SAIDI.
So the SAFE and the SAIDI were the incentives that were that we factored into the business case, which were the stiffest incentives for that particular utility.
If I can add another bit as well to that, I think it's highly dependent on where you are and under which regulation you fall into. So like I know in New Zealand, for example, under their regulation, SAIDI and SAFE used to be separate as two separate incentives, and it's someone been combined together now where SAFE doesn't necessarily have a financial incentive anymore. It was considered a bit of a double up, I believe, by the Commerce Commission in New Zealand. And that's not the case here in Australia. So it really depends on where you are in the world. Okay, I think it's safe to say we don't have any other questions now. So again, thank you very much, everyone. And we will see you on the second part of this webinar series. Thank you.
Thank you.